Hi, I'm Daniel from the Singapore University of Technology and Design, and today I will be sharing our work on the central pattern generator based control strategy of a nature inspired unmanned aerial vehicle. Let me start off by introducing the platform that this work is based on. The inspiration of this platform comes from the falling of the maple seed, which gradually falls to the ground via autorotation when released from a height. Mimicking this spinning motion, our platform generates lift by spinning its entire body around the central axis. The advantage of having a dual-winged configuration is its multimodal capability, being able to transit from a spinning hovering mode to a fixed-wing mode and vice versa. In the hovering mode, the craft is controlled by timing the deflection of the flaps similar to a helicopter's cyclic pitch. In the cruising mode, it flies as a tailless fixed-wing configuration which is electronically stabilized. This work focuses on the hovering mode of this platform. Presented here is a visual summary of the flight envelope of this dual-wing platform and where the scope of this work fits in. Also listed here are the other previous works that were done on this particular platform. The focus of this work is the application of a central pattern generator or CPG based control strategy to the hovering mode of the platform described previously. CPGs are able to turn simple control signals into complex periodic actuator commands, for example, in walking gaits and respiration processes. It has been widely utilized in the field of robotics, ranging from an amphibious swimming robot, bipeds, or a salamander robot that is capable of transitioning from swimming to walking. It has rarely been used for flying vehicles, if at all. However, given the oscillatory nature of our UAV platform, it opens up the possibilities of using a CPG for its control. Thus, our contribution in this work can be summarized as follows: the formulation of a CPG-based control for the platform, determining the CPG parameters via optimization and simulation, implementation and verification on a real-life prototype. Let's take a moment to go through the dynamic model of the UAV platform. We start with a free body diagram of the UAV, the sum of forces and moments, as well as the standard 6-Dov rigid body equations. Fm1 and Fm2 refer to the motor forces. Fw1 and Fw2 refers to the wing aerodynamic forces. Wb refers to the force acting on the UAV center of mass due to gravity. Mw1 and Mw2 refer to the resultant torques on the UAV produced by the wing aerodynamic forces. Now I would elaborate on the aerodynamic modeling of the UAV. The lift and drag forces for each wing are determined using blade element theory, where the wing is divided into elements. The individual lift and drag forces of each element are then summed up over the entire wingspan. Here is the diagram of the single blade element, together with its respective lift and drag equations. dA refers to the area of the blade element, and CL and CD are lift and drag coefficients as a function of the angle of attack and flap deflection, which is determined by a lookup table of empirical data. The total aerodynamic force and torque of each wing is then determined by summing up the contributions of all the blade elements. Now, let's move on to the formulation of the CPG. The CPG is utilized to translate higher level motion commands to lower level oscillatory commands. The formulation that we use in this work is based on the Kuramoto model of coupled oscillators. On top of the two wing flap oscillators, we introduce an additional pacemaker oscillator for synchronization with the UAV heading, bringing the total number of oscillators in our CPG network to 3. The differential equations governing the Kuramoto oscillator network are shown here. Phi refers to the phase of the ith oscillator, Ri refers to the amplitude of the ith oscillator, omega I is the intrinsic frequency, Ri the target amplitude, and tau r the gain which determines the speed in which the amplitude of the ith oscillator converges onto the target amplitude Ri. In the extension of the oscillator network, which includes the pacemaker, there are additional terms in the phase equation which determine the relations of the oscillators to the pacemaker. Psi I is the target phase difference of the ith oscillator with respect to the pacemaker. Lambda I is the strength of the influence of the pacemaker on the other oscillators, and gamma ij is the strength of the influence of other oscillators on each other. The higher level locomotion commands are designed such that they directly represent the movement in the xy plane, with a command of u equals 1, 0 corresponding to move right, and u equals 0, 1 a move forward command. To cause the UAV to move in the intended direction, the phase relations between the oscillators and the pacemaker can be varied. The commands map to the target amplitude via this equation, and the pacemaker to flap oscillator phase relations via this set of equations here. Now, we formulate that psi01 and psi02 are parameters that need to be determined for the CPG to produce the intended motion in the UAV. Before we move on to the overall control architecture, I would first introduce the concept of the UAV's tip path plane or TPP. We define the TPP pitch and roll angles as measured from the normal vector of the UAV relative to a non-rotating reference frame coincident with the body frame of the UAV. The equations to extract these pitch and roll angles are displayed on the right. Here is the full control architecture for position control of the UAV. The XY position control is made up of two cascaded controllers, one of them containing the CPG network. The Z altitude control is formulated in parallel, mirroring the architecture similar to traditional quadrotors. Inside the TPP-CPG controller, a PID controller is implemented to maintain the desired TPP angles, in which the output is fed to the CPG to convert the locomotion commands to oscillatory actuator outputs. As shown, the CPG parameters to be optimized are located here. An optimization routine is then set up to determine these parameters. In simulation, a move right command is sent to the CPG, expecting the UAV to move to the right in a straight line along the x-axis. Mathematically, the objective function to be optimized is shown here. We set up the objective function to maximize the final x position while minimizing and penalizing any movement in the y direction. The optimization algorithm that we use is PGPE, or Policy Gradients with Parameter-Based Exploration, a type of evolutionary algorithm. The population size used is 24 and run for 250 generations. The initial standard deviation is set to 2.0 and the learning rate is set to 0.01. The average episodic reward progression across the generations is shown in the middle. And here are the final parameter values determined by the optimization. Here are the simulation results of using the determined parameter values. On the left are the plots of oscillator phases, flap commands, and the XY position. As expected, the UAV moves to the right as a result of the given command. The flap commands can be seen to smoothly increase in amplitude when a command is given, characteristic of a CPG. Here we compare the simulated UAV motion using the non-optimized values together with the optimized values. Our control strategy is then implemented and validated on an actual prototype. The prototype consists of a central hub attached to the two wings. The central hub has motion capture markers which enable it to be used with a mocap system. On the right is a table of the prototype's properties and components used. Our experimental setup consists of an OptiTrack system which is used for state estimation. The controller runs on a workstation running ROS, which takes in the state data from the OptiTrack system and transmit actuator commands to the UAV via Wi-Fi. On the right is a photo of the flying space used for our tests. We first test the move right command as tested in simulation previously. As seen from the video, the UAV successfully moves as intended. A simple hovering test was done to demonstrate the controller's ability to keep the UAV in a fixed position. We then subject the UAV to a 3D ellipse tracking test, where the X, Y, and Z desired positions are constantly changing. This showcases the ability of the controller to continuously track the position in 3D. As seen from the video, the UAV manages to track the 3D ellipse. From the results, we can see that there is some sluggishness in the X and Y axis. We suspect that this is due to the constantly spinning nature of the UAV and it being under-actuated. To summarize, a CPG based on the Kuramoto model for control of a dual-wing nature-inspired UAV has been formulated and implemented successfully. It is somewhat apt that we take a nature-inspired control approach for a nature-inspired platform. Future work will involve further optimizations and experimenting to trigger different types of maneuvers from the UAV. That is all for my presentation. Thank you for watching.